Okay, so today we are working out of 12.1, and we're going to talk about the difference between a sequence and a series, and then how we use a sequence or a series to solve some problems. This is really a foundational idea for things that are applied in calculus and certainly in college algebra and pre-calculus. So realize that some of this may not seem like it has a direction right now, but that's because you can't see where we're headed. And for me to describe that to you would be a little bit complex. But the idea that we're shooting for is how can we take a pattern of numbers and continue that pattern or add all those numbers up. It seems like a pretty basic idea, but we're going to use different notation to help make it condensed and straightforward. So first thing we need to understand is a sequence is a set of numbers that come from using positive integers as inputs. So a good example would be like y equals 2x. The problem with this is that I can use values like x could equal 1.5. And that's not a positive integer. It's positive, but it's not an integer. And so if I put this in for x, I'd get 3 for y, okay, and I'd go along my merry way. That works for functions that are just linear or polynomial functions. When we talk about a sequence, we're saying that we're only allowed to use positive whole numbers or integers. So that means that we might write the equation more like a sub n equals, and that was 2x, we'd say 2n. And the reason we use n is what we call the natural numbers, which would be 1, 2, 3, dot, dot, dot. It's your counting numbers that you'd use to count items. And so we'd plug it in, and we would get very specific values that come from these whole number integers. A series is just the sum of those elements or those pieces in the sequence. If I take and I add up the first 5 terms, that would be a series. So we're going to look at 2 different types of problems. Well, I guess there's 4 types of problems, but there's a sequence versus a series. So on number 11, all it asks me to do is find the first 6 terms. Well, n has to be a whole number and it has to be positive. So the first option would be f of 1, then f of 2, f of 3, f of 4, f of 5, and f of 6. If I put 1 in here, I get negative 4 over 1, that's negative 4. If I put 2 in here, negative 4 over 2, it's negative 2. Negative 4 over 3 doesn't reduce. Negative 4 over 4 is negative 1. Negative 4 over 5 does not reduce. And negative 4 over 6 is negative 2/3. And there we are. It's pretty straightforward. First section, just plug them in. When we get to 25, we're trying to reverse this. We're trying to create a rule so we can find that last term, the next term rather. And first thing we typically look for is what's the gap? Well, the gap between the first is 3, then it's 5, then it's 7. Because the gap is changing, it means that this has got to be an exponential problem, meaning that there are exponents involved in the equation. And so if you looked at the other one, it was a division problem. There wasn't any big deal, and the gap between these actually stays consistent, although it's hard to work with as a fraction. It is consistent. Here the gap is changing. So I'm thinking of exponents. Then I look for things that are consistent. I notice that the 0.2 shows up in all of them. So I'm going to ignore that 0.2 because that could always be added or subtracted at the end. So what I'm going to do is I'm going to look at the numbers 1, 4, 9, and 16 and ask, is there something special in these numbers? Is there a pattern now? Well, the pattern's still 3, 5, 7. But at the same time, I know these are special numbers because they are perfect squares. So this is like 4 squared, 3 squared, 2 squared, and 1 squared. And since this is the first term, n would be 1. Second term, n would be 2. N would be 3. N would be 4. Pretty soon we're seeing, hey, that 1, 2, 3, and 4, those are really n. So we have n squared. Okay, and that's going to produce 1, 4, 9, and 16. But then I still have to count for that or compensate for the 0.2. I need to be bigger, so I'm going to add 0.2 to the equation. And now I'm done. That's not the easiest problem to get through, but let me know what you need. Okay. 39, we've changed from a sequence to a series, as evidenced by these addition signs. Now we're trying to add all of these values up. The first thing we need to do is find the pattern. Well, the pattern here is a difference of 2. And it gets 2 bigger, 2, and 2 again. So I'm seeing this consistent pattern of multiplying, of adding 2. So I'm going to put 2n. Okay. Whenever you see that gap being consistent, that goes with your n. And then I need to compensate, because if I put 1 in for n, I would get 2. But I want to know, what do I do? Okay, what do I do to that to equal the negative 1? Because this is my first term, this is my second term, third term, fourth term, fifth term. So the question is, what do I do with this 2 to get negative 1? The answer is I need to subtract 3. Okay, so we're going to go ahead and put minus 3, and we'll put minus 3 up here. 2 times 1 minus 3 is negative 1. 2 times 2 is 4. 4 minus 3 is positive 1. If I come down here to the seventh number, it's a 5. 2 times 5 is 10. Minus 3 is 7. So this is my rule, my equation that I'm going to use. Now all I have left to do is to put it into summation notation. That's kind of fun to say. We use the sigma for summation of 2n minus 3. But I have to be able to tell people, what do you put in first for n, and how far do you go before you're done? My first my first value, negative 1, comes when this equation uses a positive 1 for n. So I'm going to say that n equals positive 1, and I want to climb this ladder all the way up until this ... that comes after tells me it goes forever. Forever is infinity. If I had only stopped at 5, let's say that I stopped right there, then I would put a 5 here instead of infinity. Okay, otherwise we're the same. And that's our answer. Number 55 is our last one that we're going to look at together. And it's actually kind of interesting because they're using the summation notation to produce a series. And it says that I need to find my terms. Now look, it goes from 1 to 25. That means there are 25 terms. So what I'm going to do is I'm going to put 1 in for I, then 2 in, then 3 in, then 4 in. If I put 1 in for I sub 1 is going to equal 1. I sub 2 is going to equal 2. Then 3, 4, all the way down to 25. Now I've got to find a way to add these numbers up. And there are multiple ways to add these numbers up, okay? So you need to understand that we do have methods, we do have ways of doing it. But for now, what we're going to do is we're just going to write them all down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. Now, when you add all this stuff up, you can just use your calculator and add them all up. There's also tricks along the way. For instance, 9 and 1, that's 10. 2 and 8, that's 10. 3 and 7, that's 10. 4 and 6, that's 10. 5 and 15, that's 20. 10, that's 10. 11 and 19, that's 30. 12 and 18 is another 30. 13 and 17 is another 30. And 14 and 16 is another 30. That's 20. And then, you know, 1, 2, 3, 4, 5. If I add those up, it's 3, 6, 10, 15. And then I've got 2, 4, 6, 8, 10. That's 100. Now if I add all these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, plus 9, so it's 19, 23. So now I got all confused. Well, anyway, we add all of them up. Use your calculator, or do it by hand. It doesn't really matter. It's no skin off my nose. But when you add them all up, you should end up with 325. All right, guys, that's what your assignment's like. Most of the time, you don't have an extensive list to write out like this, and we're going to learn shortcuts for that before we're done. But hopefully you do well, and I'll see you in class.